Welcome to Algebra 2, Semester 2. This is the final lesson in Unit 8. It is factoring 4 items and then sections 11.3 and 11.4 out of our book. So first thing, let's look at factoring the 4 terms. Factoring 4 terms is really like factoring 2 by 2. I underline the first 2 and just take the GCF out of them. So taking the GCF out of 12 and 8, well, 4 would go into both 12 and 8. So I write a 4 out to the front. As far as the variable, the lowest exponent is x squared, so we pull that out. 4x squared times what would give me 12x cubed? That would be 3x. 4x squared times what would give me 8x squared? That would be a minus 2. Now I take that binomial and I write it again right over here because I'm wanting to eventually factor that out. So I need those identical. Now I ask myself, 3x times what will give me 3x? Well, that would just be a plus 1. 1 times negative 2 gives me negative 2. So I know that I have that. That's the first step. I want to go through the first step on all of these and then we'll go back and do the second step. So let's look at the next one. We underline the first 2. 2 would go into both 6 and 10, so we pull a 2 out front. You want to always get as much as you can out of them. They don't both have m's, so we can't pull an m out, but they do have p's, so we'll pull a p out. So that leaves us with 3m. 2 times 3 is 6. M times p is mp. Minus 2 goes into 10 5 times. 5 times 2p is 10p. Now we take that binomial and we write it again right here. Now we ask ourselves, what times 3m will give me 18m? That will be a plus 6. Now I make sure that it works for the second term. Positive 6 times negative 6 is negative 30. Very good. Now we go to our next 2 by 2 and we look at what is common here. We have x is common. The lowest exponential on the x is squared, so it's x squared. X squared goes into x cubed, x times. X squared goes into a positive x squared y, y times. Now we take that binomial, write it again right over here, x plus y. And now we ask ourselves, what times x will give me a negative xy squared? That would be a minus y squared. A negative y squared times a positive y would be a negative y cubed. So that does work. Now I need to take a quick peek and see if I have you go through the next phase here. Yes, I do. I want you to go ahead and do the final step here, which is to factor one more time. And this time, factor out this binomial that's the same in both halves of that expression. So we factor out 3x minus 2. And then what we have left would go in 4x squared plus 1. Now the cool thing is, if you were to multiply this back together using FOIL, you would come out with the 4 terms that we started with. Remember, factoring is the opposite of multiplying. Or maybe I should say it's the reverse of distributing and multiplying binomials. So if you want to check these, FOIL this, you'll get what you started with. When you're factoring, you're just trying to pull out of the expression that's there. So pulling out of the expression here, we see 3m minus 5 in 2 locations. So we're going to factor that out. 3m minus 5. Then we have 2p plus 6 left. And that is factored. Now, when you factor these, one thing you want to look at in these binomials, is there anything else that could come out in case you possibly missed anything? When you get to this one, do you see how it's got a 2p and a plus 6? You could pull 2 out of each of those. So in doing that, we factor out again 3m minus 5, pull the 2 out, that would leave p plus 3. Now, we do not like to leave just a number in the middle of binomials. It gets a little bit sloppy looking, so we always move those monomial or single, it wouldn't really be a monomial, but move that single term out to the front and just rewrite your binomial factors after it. Okay? The last one here, x plus y, we factor out. And then we have x squared minus y squared. Now, that should look familiar to you from our last lesson. That's a perfect square. That's a perfect square. And it is a difference. So we can do the difference of two squares, which you would remember has a plus and a minus. And then we take the root. So the root of x, the root of y. And now we look at our answer and we notice we have an x plus y and an x plus y. Well, how could we write that so that it's a little bit neater? If you said by squaring it, then you were exactly right. And that would be our final answer to that factoring problem. Okay, that's the bottom of page 11. Now moving up to the top of page 12. I wanted to look at some patterns that occur here when we're multiplying some binomials. X minus y, if we take that 3 times, I wanted to show you that it's not the same as what you looked at yesterday where it's x cubed minus y cubed. And if you remember right, that would be x minus y times x squared plus xy plus y squared. And I just want you to see that the pattern's not the same, that this does not mean the same as that. What this actually means, when we multiply this out, is we get, and there we're factoring, but if we multiply that, we'd get this. Here we're going to multiply this, x minus y times x minus y times x minus y. FOIL this, x squared minus xy minus xy plus y. Now we're still multiplying this by x minus y. So x times each of these terms, that would be x cubed minus x squared y minus x squared y, we could have combined those two, plus xy. Now we take the y and multiply it by each, we get a negative x squared y, a negative negative xy squared, which I don't see that on here, negative xy squared, negative xy squared, and then we have a negative y squared. I've made some kind of a mistake here. Oh, I see. This should have been a y squared when we multiplied y times y. So that would make that a y cubed. And it would also cause this one to be xy squared. Okay. So let's make sure that we have them right now. Negative x squared y, and then a negative xy squared, a negative xy squared, and a negative y squared. Okay, this looks a little bit better. So now we bring this down, we've got x cubed. We have 3 of these negative x squared y's. We also have 3 of these negative xy squareds and a minus y cubed. Sorry about that. That got a little bit confusing where I didn't combine those, and you can see in the next one, we'll combine those like terms before we go further and multiply it. So let's see if this one looks a little bit cleaner. Again, I don't edit the videos because I want to see you see me make mistakes and know that I'm human as well as you. So x plus y, and x plus y. Okay, let's FOIL these last two, and then we'll be able to FOIL that one off the front this time. That should clean it up a little bit. X times x is x squared. Then we're going to have x times y, which is a plus xy, and a y times x, which is a plus yx, but we'll put it as xy to easily combine those two, and then plus y squared. Now let's go ahead and combine these this time. We have x squared plus 2xy plus y squared. Now we multiply by x plus y, our other term that we're bringing down. So x times x squared is x cubed. X times 2xy is 2x squared y. X times y squared is xy squared. Now we take y times x squared is x squared y. Y times 2xy is 2xy squared. Y times y squared is y cubed. When we add those together, we get x cubed plus 3x squared y plus 3xy squared plus y cubed. So you can see how these end up different from that situation. So I just wanted you to see those patterns and kind of become familiar with them. Now today we're looking at normal distribution, areas under a normal curve. I linked Mr. Nydstrom's video into this unit so that you can study a little bit more about what standard deviation is. This symbol we call sigma, that little symbol there, and this sign for the mean, bar x. We also have a symbol in these illustrations where it's mu, and you need to get used to mu. You can remember it because it looks like a M and a U put together, so we just call that mu. So we look at this distribution curve first off, and what I'd like you to understand is that if we were to make, let's say, a histogram of the data, this is how your bars would add up, where a majority of your data falls within just a very short distance of your central tendency here in the center, near the average. So if it's a normal curve, we actually know that 68% of the data falls within this first deviation, or the first section above and below the average. So we'll talk a little bit in class on those. I just wanted to show you how you work these problems. Here it's asking what is the probability of all the values less than or equal to the mean. Well, if you know that your middle point, that your average is right here, everything below it on a normal distribution curve would be 50%, because 50% is above and 50% is below. Now, in order to prove that, you could actually take these percentages that we have on the graph, and you could switch them back to decimals or keep them as percentages, and show that 34.13 plus 13.59 plus 2.28 equals 50%. Okay? Now, the next one is asking, what's the probability that the values are within 2 deviation standards, or 2 sigma there, less than the mean? Okay, so we want to know all the values within these 2 sections. Well, again, it's 34.13 for the first one and 13.59 for the next one. Add those together and you've got the percentage. It's about, I'm just taking a guess, about 47.5%. Okay, you can add those up specifically once you turn off the video. I'm just kind of guiding you through this. Here we're asking what's the probability within 2 deviations above the mean. 2 deviations above, well, it's going to be exactly the same as the 2 below. So it would be, again, 47.5%. Now, there is something that we do, rather than writing out all the time that this is mu minus 1 sigma, mu minus 2 sigmas, we can just simply go with what we call a z-score. A z-score is a z-value that's given to the x value. It's the number of standard deviations the x value lies above or below the mean. So in other words, this was 1 deviation below, and here on this graph we're going to show it just as a -1 because that's the z-score. In class we're actually going to use z-tables to look information up, but I wanted you aware of z-scores and that they're just speaking of the number of deviations from the mean. So that's page 12. Page 13. We go into looking at bias sampling. This is how we gather data from different populations. This is the top of page 13. There's four main different types of samples. There's self-selected sample, which are members of the population volunteer to be sampled. I'm not going to write these in, just rewind the video and take notes from what I say. Self-selected are members in the population that volunteer. They volunteer to be sampled, so write that in right there. The next one, convenience sample. These are your easy to reach members of the population that are selected. They're real easy to reach, it's convenient for you to sample them. Systematic sample is when you have a rule that you go by. A rule that you go by to select members out of a population. Okay, you might say, you know, every 4th person through the door, or every other house in the neighborhood you're going to sample from. A random sample is each member of a population has an equal chance of being selected. Okay, so pause the video, write those in there. I do expect you to have them written in your notes. Here's 2 scenarios. You want to survey students here at school, and you contact students who you have cell phone numbers for. Which would that be? Well, they weren't self-selected because they didn't choose. And it's not systematic, you're not following a rule. It's not completely random because you're choosing out of convenience. So it is a convenience sample. Okay, next one. You mail surveys to all the students and collect data from the surveys returned to you. Well, that wasn't very convenient this time, was it? If you mailed them to everyone, it's not random because everyone got one. It's not really systematic because you're not saying that you're going to mail them to a certain number of students or that you're selecting just certain ones as they're returned to you. It is a self-selected sample because though you mailed to everyone, They chose whether or not to respond, and so they selected themselves as being part of your sample. So that is self-selected. Okay, next up, seeking swayed survey results or seeking true representation of the entire population. That's the difference between biased and unbiased. Unbiased means that you're seeking a true representation of the entire population. A biased means that you're trying to sway the results. Politically, a lot of times this occurs right now. There are just a number of surveys that are taken where you've got to really look closely at what was the population that they chose. Oftentimes self-selected populations are chosen, and the propaganda coming out with the survey causes certain people to respond over others. Okay, the margin of error formula. This is a formula that we have to know, well, how big is the error in the statistic when we're looking at it? So if we use this formula, for example, and I tell you I have 100 people that I surveyed, and 100% of those people said that they would prefer to be in school Monday through Friday instead of our normal 4-day week. So you could figure out, now that's not true, I'm just making that up, and I thought that would catch your interest. So in order to tell me what the chance of error is here, I would plug in to this formula and say that's plus or minus 1 over 100. Now, actually, let's say that I said 50% of people said that they like Monday through Friday option rather than Monday through Thursday, because I don't want to confuse you with the 100% and the 100 people. So our margin of error is 1 over square root of 100. That would be plus or minus 1/10, or plus or minus 0.1, which is plus or minus 10%. That's the margin of error. Okay, so I should have put plus or minus 10 people there. That would be 10%. So if I say 50 people would prefer Monday through Friday, that could be as few as 40 or as many as 60. That's what that's saying. So we come down here to the next question. Now if we survey over 1,000 people, and 52% indicate a certain answer, then what's the margin of error on that? Well, that would be 1 over, again, our population sample, square root, 1011, and that equals approximately, put it in a calculator and divide 1 divided by square root 1011, and you'll come out, you'll have to round it off, it's approximately 0.03, so it's approximately 3%. We could go one more if you wanted, 3.1. So if we look at our margins, I said it's 52%, so minus that 3.1% error, it could be as low as 48.9%. Or if we add that, which is the other direction the error could go, it could be as high as 55.1%. So converting that into the number of people, so 0.489 times 1,100 or 1,011 could be as few as 494 people. Now if we take this 55.1% and we convert it to a decimal, 0.551, and multiply it by 1,011, we find that it could be as high as 557 people. So we have a little bit of room there that shows that there's error. Did you notice how when we get larger numbers, we get a smaller percent. That's why we try to have larger data groups anytime we're trying to get information, because 10% is quite an error. That's quite an amount of error that we could have. Whereas 3%, we've reduced that significantly. That's a pretty good indication of our population. The larger your sample, the better understanding for the population that you're going to get. So now we look at what if you're told that you have a margin of error of 5%. Can you figure out how many people were surveyed? Well, we go back to our margin of error formula, and we know that plus or minus 1 over square root of n equals 0.05. Well, if that's the case, couldn't we square each side to get rid of that square root? So if we square each side, 1 times 1 is, let's just put in the squares so we know what we're doing here. So if we square this, the plus or minus is going to be eliminated. 1 times 1 is 1. Square root of n times square root of n would be n. And we get 0.0025. Now we just go ahead and we clear out the fraction, multiply each side by n, and we get that canceling, and we get 1 equals 0.0025 times n. Now divide each side by 0.0025, and we find that, whoops, we shouldn't have divided by 0.0025 n, we're trying to get n alone. And we find those cancel, and we find that n equals 400. Make sure that you plug that into a calculator and see that it is 400. So that tells us what size population we were gaining information from. That is the end of that section. Thank you very much.